52. So if you are less than 52, you need to work harder, but don't worry about that, because if you can participate in this class, you will get other bonus, and also because some of you purchased the textbook, so you have some extra bonus from that. Don't worry about that. 52 actually it's good. I would think that this class is not we call 营养学分. No, of course not. This is a graduate level class. So I think 52 is acceptable for me. But most of you still have some, I think for some maybe didn't get used to be so accurate to do something. You think, okay, in practical maybe we can use some approximation, it's okay, but for microwave engineering that's not true. Okay, so all of you need to get used to first the definition, which I insist all of you to understand about the definition for all the notations, all the rules for different conditions. For me, I only teach you all the most important fundamental theories. Okay, in microwave engineering, you can also refer to your textbook. You have textbook. You have my video on YouTube. You can rewatch. And here I will give you some quiz. If I think those maybe it's very difficult to understand. Okay, you need to keep trying to understand microwave engineering. Okay. For some of you, maybe you have a question about your score. You can make an appointment with me to see your midterm exam. But if you think, what?
Can we check the answer paper?
The check answer. I will discuss with you, and maybe we will make an appointment in my office. Then I write down some of when I give you score, I write down why you make mistake. You just come to my office, but it depends on how many people you need to come to see your midterm exam. Okay. I will give you time to maybe you think about if you want to see your midterm or not. I will. In the end of this week, we can make an appointment. Okay, just come to the office and maybe just spend a couple minutes to check that it's fair or not. Okay. Okay. For today's class, we are entering the most important part. Before the midterm, it is just like an introduction about electromagnetics. But now it is more important. Now you can see what we are doing. Okay, so this is a microwave transmission line for chapter 2 and chapter 3. We are talking about our microwave transmission line. For the chapter 2 is about the theory, very theoretical materials about theory. I'm going to tell you about the fundamental, the most general, most basic, high frequency theories about the microwave transmission line. Okay, high frequency transmission line. This is a high frequency transmission line connected to our VNA, and you can use this transmission line to measure up to 20 gigahertz, hopefully, to measure. Okay, just from DC to 20 gigahertz. Okay, the price of this transmission line is about, anyone know? For this line, it looks just easy, the same as the common transmission line. I bought this transmission line from Huang Liang. Okay, we have some project, we work together. They sold this transmission line in like 5,000 NT dollar. Just this. You think this is maybe you don't see different about this transmission line. This is a coaxial line. Maybe do you want to come here, or you are anyone? Most of you are familiar with, especially you. You don't know about our transmission line, right? But for other students, do you want to come to see? Okay, maybe Abi or maybe all of you. Just come. All of you come. You don't need to. Maybe we can spend some time to learn what we are doing. Okay, don't touch it because $5,000 NTD 5,000. Okay, so yeah, come closer if you maybe all of you can measure it, right? But you don't have, maybe you don't pay attention about what is inside, why it is so expensive. You can see there is a conductor outside. Pay attention that I don't touch it. I touch this outside. When I touch that inside, this line is damaged. $5,000 is gone. Okay, don't touch inside. Okay, this is a coaxial cable. Coaxial. Why we call this is coaxial? You can see there is a pin inside there. Did you see that? There is a pin.
Center.
This is the signal line inside. And did you see there is a white dielectric? Why we learn dielectric? Epsilon R equals to maybe 2, maybe 4. Remember epsilon R? If you see the white material, you see the white material between two conductors, it is dielectric. Okay, and also there is the outside, it is a ground. It is ground. So this is a coaxial cable, a very typical type of microwave transmission line. When you want to connect a line to another, there's a screw. See that? There's a screw. We said this is a male. This is a female. You put that here, connect that, and you turn this carefully.
We will use
yeah, of course, you need to use a screwdriver and do that carefully. Okay, don't do that. $5,000 will be gone. Okay, do that very carefully. But of course, you don't connect this terminal to this terminal. You connect this one to maybe machine, or maybe you connect this to machine and you connect this to your circuit, your DUT. Okay, this is a transmission line. And for chapter 2 and 3, we are going to study a transmission line. Okay, this is one of the typical transmission line. This is a coaxial cable, which is more expensive, and I bring more. Okay, this is a typical transmission line. I call this microstrip transmission line. Actually, it has two connectors at the both ends. We need these connectors to connect to our cable and connect to our machine, our VNA. Okay, this is a microstrip line, and my microstrip line here is manufactured on my PCB, printed circuit board. Maybe the material it is FR4. I have epsilon r equal to 4.2 to 4.3. Okay, this is one of the typical microstrip line. Why we make this, but we don't make this? Because it is easy to make from our lab. We use the machine to etching
Curving.
the surface. Yeah, curving. Yes, yeah, the same. We take the connector, the top connector outside, and we keep the ground here, and we connect our ground to the ground of the coaxial connectors. Okay, so this is another high frequency transmission line. This is easy to calculate coaxial cable because this is TEM mode. This is harder because this is quasi-TEM mode. My microwave will leak. There will be some leakage of microwave outside this material. So we will use the numerical result to calculate our microstrip line. Okay. What is the most difficult? It is waveguide. Okay, this is one example like my waveguide. This is also one section of our high frequency transmission line. This is half wavelength. We use the half wavelength micro waveguide cavity as our resonator to design a filter. This is a microwave filter. Okay, this is one of the example of the waveguide. This is also the transmission line. So here we have three types of our high frequency transmission line, okay? But in chapter 2, we try to find a general solution of all the high frequency transmission line. In chapter 2, actually we are talking about this, and this, but you don't see the real transmission line in chapter 2. You will see the real transmission line in chapter 3. Okay? Do you know what's the difference? In chapter 2, we talk about the basic, the fundamental theories in chapter 2. But in chapter 3, we will transfer all the theories in chapter 2. We mapping this general theory to different kinds of transmission line. I will focus on these three kinds of transmission line in chapter 3 because you can see them in our lab. Okay. Of course, you can map the same theory in chapter 2 to any other high frequency transmission line in your future if you will need. Okay. Okay. So, okay, you can go back to your seat. So I'm going to talk about a general theory. Yeah. Maybe next time if you have the opportunity to see the detail about our coaxial cable, it looks maybe expensive because people make it. Okay, maybe you think looks maybe not so beautiful because students make it, but you can still make very beautiful microstrip line if you find some company can help you for manufacturing. It's okay. Okay. The theories are the same. In school, we teach you all very simple theories. Okay. Please read your textbook chapter 2 for this part, okay? Chapter 2, if you have a POSA, read that. And I will tell you the most important things about transmission line. Okay. I show you the outline of chapter 2. Those key, those important parts, I think most of you should understand. Okay. First, lumped element circuit model for transmission line. Lumped circuit. About our transmission line, how to describe this transmission line. In our department, we always, usually, the first equation we learn related to our department, electronic engineering. Maybe you will want to know the first equation, maybe V equals to IR, right? V equals to IR, or maybe P equals to VI, right? The first two equations you learn in our field. Both of these equations, they have voltage and current. We have voltage and current. Okay. So, how to describe what happened, our performance of the circuit, or what we measured? We try to find out what is the voltage and the current on the transmission line, V and I. Okay, so it looks like a new start because voltage and the current I didn't mention a lot before our midterm, right? I didn't mention. In our midterm, we always works on E field and H field. You say, yes, we don't need to care about E and H. You are totally wrong. Before our midterm in chapter 1, that is an important introduction to describe voltage and the current. Why? Let's look at the unit. What is the unit for E? I think all of you now remember, right? What is the unit for E?
V per meter.
V over M, right? And for this one is ampere over M. So see, the unit for voltage is volt, and the unit for the current is ampere. You see something connected between voltage, current, and H field, E field, and H field, right? Now you understand why I always encourage you to write down the unit for every character, for every notations. It is important to help you to remind you to understand what they are. So, to understand something similar to them, I try to understand what is the voltage and the current for our high frequency transmission line. What can we use? What can we use? We try to apply some old theory you should already knew, okay? What? For example, we use resistance R and maybe Y, call this, how call it? The meters? Resistance, no, wait a moment. Y, G, and maybe L and C. Okay. We use inductance, capacitance, resistance, G 好好的 G is 1 over R. Okay. Okay, we use this, something we knew this before, to describe my voltage and the current. Okay, this is what we are going to do for the first part in chapter 2. Okay, we call this is a lumped element circuit model. Okay, we use this to describe our voltage and current. We call this lumped element circuit model. This is for the first part. Okay, and the second part in chapter 2, we already have the model. We know the voltage and the current and the R, G, L, C, the relationship between voltage and current and those lumped element circuit model. We knew that. What we are going to do is we connect this line to something. Okay? We connect this line to something. So this line, maybe you can connect to, okay, another circuit. And this circuit, maybe we connect a short line. We connect to a load, or we don't connect, it's open. We connect to some resistance. We call maybe load. Okay? So this is what we are going to do. We use this model, apply the result of this mathematical model to some terminated transmission line, and we also use lossless because we want to simplify the result. We don't see the loss, okay? It's a good thing, right? It is a very good thing. We consider only lossless at the beginning. Okay. So this is terminated. Terminated means your another end is connected to something. And then we find out what happened if I connect to something, what happened to the input end. Okay. We try to calculate what happened at the input end, and I connect this transmission line to something. This is the second part. And we try to find out a general impedance equation. If I connect to something in some condition, what is the new input impedance at here? Okay, this is the third part of chapter 2. Maybe, and this is the last part. I will not spend too much time at the quarter wave transformer. We will spend more time for the Smith chart. You guys know Smith chart, right? There is a metallic symbol. You see this a lot when you are talking about high frequency transmission line. You will see this figure many times. When you say you are an RF engineer, you go to find a job, your advisor will ask you the question about Smith chart to make sure you understand or not. Okay, so I will spend more time because this is job related, right? People like to ask you this one, and you understand that. You know many. Maybe you are qualified RF engineer. Okay, so 1, 2, 3, 4. Those 4 topics are the most important topic in chapter 2. Okay, you can also read your book to see what happened, what Posa said. Okay, maybe he used different way to explain these four topics. Okay. For the first topic, okay. For the first topic, I think I don't need to explain what is microwave again. Okay, in the textbook they tell you what is a microwave. The microwave means the frequency, the signal frequency on your transmission line is higher than 3 multiplied to 10 to the power 8, or I say 300 megahertz to 300 gigahertz. Okay, the range of microwave. The frequency is very high on this wave. So something is different. You need to be very accurate to understand what happened to microwave. In DC, your frequency is 0. If your frequency is 0, all the connectors, there is no dimension. It's shrinking to only one point in DC. So in DC, you connect all the connectors together. You don't need to consider your high frequency. But when your frequency are getting higher and higher, which means your transmission line is getting higher and higher. There are more and more wavelengths for the same physical length of the transmission line. If your frequency is getting higher and higher, so very high, if your frequency is low, maybe this is half wavelength. But if your frequency is getting higher, maybe there are 10 wavelengths on this transmission line. So something will be different. Okay? So frequency matters, and if you have textbook, they try to draw high frequency transmission line on your 2D textbook. Okay, so for coaxial line, he's trying to draw the cross section of the transmission line. Okay, this is this one, the same, totally the same. This picture is this transmission line. Okay, he draw the cross section. You see there is a connector. This is a signal connector inside, and this is ground, and this is your dielectric material. Okay, those 3 important things in this structure. But in the real world, it's not that simple, right? You can see many different things. Like for the outside ground, you have different structure to make it more reliable, right? And for the inner, these 2 terminals, you will see there are screws to help you to connect tight. right? There are more and more details in the real world, but in our theory, we consider only these three parts for this coaxial cable. Okay. About microstrip line, you also see the microstrip line here. There is a signal line on the top of the material, and then there is a ground in the bottom, right, for a microstrip line. But there is a more fundamental high-frequency transmission line. We call that strip line. You put your signal line inside the material, and then there are two grounds on the top and in the bottom. This is also the TEM mode, easy to calculate, but this is hard to fabricate, right? It is not easy to put your signal line inside the material. For this, it's easy to fabricate. This is not easy to fabricate, okay? So we talk less and less in school, but maybe in the industry, maybe you can see this line in the future. Probably, I don't know. There are many possibilities. We can also put the ground to the both sides of the signal line. Okay, if this is the signal line, we refer to our microstrip line. You can put your ground on the both sides of this one, and then you put a material here. We see this a lot, but we don't make it. Actually, we make it. What is this? This is the transmission line on your IC. On your IC, okay? When you manufacture an IC, there are 3 pads for high-frequency transmission line input. There are 3 pads. One of the pads is the signal line, and there are 2 grounds on the both sides. This is the IC, the input of the IC. Okay. So transmission lines, and you can use. This is a 3D point of view to see this transmission line. For this one or this one, it is also a coaxial line. It's not just a cross section. It is, you see that in a different view, you can see XYZ now, okay? Okay, for this one is coaxial line, and this is your microstrip line again. You see not only this part, you see more about your microstrip line. And this is a waveguide. You have only one metal. It's very special high frequency transmission line. Okay. So for all of this high frequency transmission line, we want to use a general Roche theory to describe all of this transmission line. This is what we are going to do in chapter 2. How do we know? Okay, it's time to start. How we start. This is a very new start. For all of the transmission line, for most of them except waveguide, we try to separate my transmission line in different pieces. I cut them. Because if this is a uniform transmission line, if I cut this transmission line in the very, very small pieces, I connect all of these pieces together, it is our final transmission line. It's okay. every pieces I chop it in a lot of pieces. If the length of each pieces is very, very, very small, I put them together. This is a uniform transmission line. Every pieces, they have the same model, okay? If this is uniform, uniform means everywhere it is the same. If this is uniform, we don't talk about the connector in the both ends. We think about the most of the transmission line. If this is a uniform transmission line, if everything on the transmission line, it is the same everywhere, I cut that, okay? All the transmission line, for most of that transmission line, they have signal material, the connector, we can support your signal. You have the connector, you can support the ground. We call the material for signal and material for ground. So we draw this transmission line like this one. This is how I draw this transmission line. Maybe you have a question. Oh, it's not that looks like, but I try to draw a transmission line which can be used for all different kinds of transmission line. Okay, so the transmission line has the signal line and the transmission line has the ground line. Okay, so this is the way I draw my high frequency transmission line. So in this class, I will use the symbol of this one. I will draw this symbol as a transmission line. Okay? Remember, this is not a couple line. I just draw my ground. This is ground, and then this is signal. Okay? And then you can regard this like my coaxial cable or microstrip line. Okay? We have a deal. Okay? I hope you understand. This is not the couple line here. You don't see, actually, it doesn't look like a real line, but I just write down this one like a transmission line. Okay? And for the transmission line, as I said, this one is my coaxial cable, and because it is uniform, I cut that in different sections, a little pieces. I cut it. I take just only a little part of this section, and if the total length of this transmission line, it is L. Physically length is L. Okay? If the length is L, I call this small piece of the transmission line, I call this delta L. And the delta L is very small. So I will write down like limit and the delta L going to 0. Is that okay? Okay, so far? Okay, so I took a little bit transmission line. And someone, he think these small pieces can be modeled by using RLGC. Okay, what are RLGC? RLGC they are the average value. Average, listen up. It is average. RLGC. They are the average value for the series or shunt resistance, inductance, and the conductance and capacitance. Okay, so G is conductance. Okay, it's good. I write it down. Okay, so I can have a lump element model to describe the small section of my transmission line a little bit. So for all the transmission line, I have a lot of this one, maybe infinite number of these sections together. For each section of that, I use my lumped element model to describe it. For a series structure, I have resistance. The total resistance is my average resistance multiply the delta Z. Okay, use Z. Let me change. Z. Call this total Z. Okay, Z is a position. Okay, it's okay. L or Z is different name. So the small position, or we call it small length of this section, multiply the average resistance, which means the resistance, the series resistance of this section. Okay, and similarly, we write down everything. Like for the inductance, you use L multiply delta Z for the total inductance of this section, only this section, okay? For the G conductance, you use G multiply delta Z, and for capacitance, you use C multiply delta Z. Okay? Are we good here? So this section is this section. Okay, I just maybe draw it a larger to help us to see. Okay, this blue box is this blue box. Okay. So what are the important things we try to describe? I hope you guys still remember. We try to understand what is the voltage and the current on this transmission line, right? Voltage and current. So the most important thing for this model is the input voltage at the input end and the output voltage at the output end. You can see the difference, right? What's different? The position is different. And here is Z. And here is Z plus delta Z, because your position is different. Okay? The voltage here and the voltage here. Also, there is a current, input current and output current. Okay? For each section, you have the input current, you have output current, you have the input voltage and the output voltage. There, the voltage here and here, they are different according to you have different position. So here you use VZ, and here is VZ plus delta Z. Okay? But at the same time, you use T here and the T here at the same time, but different position for the voltage and the current. Are we good here? And we can start. Okay. We try to use the Kirchhoff voltage law and the Kirchhoff current law. Okay. So I think most of you need more extra point, right? So can anyone, actually I write down the answer here, but can anyone help other people to understand, to describe the Kirchhoff's voltage law on this figure? Extra point today. Can anyone? Kirchhoff's voltage. Do you know, you guys learned this before, right? In 电路学, right? Kirchhoff voltage law. Anyone want to try? Do you have extra point for today? Anyone? If you worry about your score, maybe you can, yeah. Make an equation which voltage equals to which voltage plus which voltage. Can anyone help? If I do that, no? Okay. Okay, maybe it's up to you. So the voltage where equals to the voltage. Wait, come here, come here. So come here. You just use your hand. Okay. Make the equation. So
this voltage equal to this plus this.
No, this voltage equals to the voltage difference between where and to where, and the voltage, okay, the voltage here, right, equals to
I plus
you just use your hand, tell me the voltage cross,
voltage plus R.
okay, and
voltage plus L. And voltage plus G.
So the voltage cross G, and so it's the voltage cross here, right?
This.
Okay, all of this. So which is the voltage?
Which is voltage?
The same as the voltage cross the conductance and the capacitor is equals to the voltage where? The voltage at the output end, right?
Yes.
Okay, got an extra point. It's not so hard, right? So for the Kirchhoff's voltage law, the voltage cross here will equals to the voltage cross your resistor plus the voltage cross your inductor plus the voltage here, because they have the same ground, right? Which means the voltage here equals to the voltage here to here. They have the same ground. Okay, let's take a break and we will continue later. So, okay, let's take a break.